What a pleasure to be here. What I'd like to do is give you a very personal view of how my career evolved, and more particularly, how I view innovation. I would say in my career there have really been a couple of dominant themes. One is complexity, and another is innovation. And these two together, as you'll see, led to being involved in a series of paradigm changes in biology that led to a new type of medicine I call P4 medicine that is proactive, and we'll describe that in some detail. But what I'd like to do is give you a sense of the historical context that led up to P4 medicine, and then give you some idea of where we think we're going to be going in the future. So this whole idea of complexity intrigued me from the very beginning of my career and starting at Caltech in 1970. And the issue was, biologically, was enormously complex. And it was obvious even then the tools we had for dealing with this complexity were really ineffective. But what was very interesting is the complexity came from really a relatively, in principle, simple source, and that was the random and chaotic process of Darwinian evolution. And what that did, in essence, was not follow the law of Occam's razor, where you create systems in the most efficient way, but it was much more like a Rube Goldberg kind of apparatus where you piled one thing after another thing, but when you got done at the end, whatever it was you were doing actually worked. The critical point then in complexity is the whole question of how you deconvolute the complexity so you can understand it. And I would argue that systems approaches to biology and medicine have really enabled us to do this, and that's really one of the purposes in this lecture, to demonstrate that to you. But let's go back to this simple analogy of a Rube Goldberg apparatus, because I think it's very instructive about what you have to do in systems biology. So here's a gadget that has 14 little entities that are tied together to be able to let Rube Goldberg cool his soup. And so the question is, if you wanted to look at that system, how would you go about analyzing it? So the first thing you do is you'd identify the individual parts and kind of try and understand what they did in isolation. The second thing you do is you'd put all those parts together so that you had the system connected in an appropriate way. Now, the third thing that's really key is you have to understand the dynamics of the system, because you don't cool a soup unless the cooling device moves. And so how does the whole system dynamically change its behavior to end up giving you the function of cooling the soup? And those really are the principles of systems biology when we think about biological systems, biological networks, as we'll talk about them. Now, in 1970, in thinking about complexity, it was obvious to me that the problem was really hard. But I did read a book that was first published in 1962, The Structure of Scientific Revolutions by Thomas Kuhn. And basically this book talked about paradigm changes and the transformational effects that they bring to whatever endeavor they're directed at. And of course, the essence of the paradigm change is initial enormous skepticism that one has to overcome. And in reading this, I realized that in biology, we really were going to need a series of paradigm changes, and at that time, I had no idea exactly what they would be, to be able to do this. And I will say, over the subsequent 40-some years, I have had the really good fortune to participate in 5 different paradigm changes. And I'll list them for you very briefly so you get an idea of what they are, and then later say a word or two about each. So the first was bringing engineering to biology. So at Caltech and even at the University of Washington, we developed a series of instruments that let us decipher biological information in more effective ways, including the automated DNA sequencer, which made the Human Genome Project possible. And the second paradigm change came as a consequence of that instrument, the automated sequencer, because I did get involved in the Human Genome Project at the first meeting held in the spring of 1985 at Santa Cruz, where 12 experts came to consider whether this was possible. And two conclusions were reached. One is it was technically feasible, though at that time extremely difficult. And the second was the 6 people were split 6-6 as to whether it was a good idea or a bad idea. And frankly, the 6 that thought it was a bad idea were fanatical about being against the Genome Project. And I'll say a word more about that in just a moment. As a result of developing the automated sequencer, I came to understand that biology in the future, as we develop technologies to be able to deal with complexity, would have to embrace a cross-disciplinary environment, bring in scientists of all different persuasions to work on technical problems in biology. And we created the first department to do that here at the University of Washington, as you heard. And of course, that set the framework then for really starting to think about systems biology, which is, as you'll see, the real key to dealing with complexity. And in 2000, we did start the Institute for Systems Biology, again, the first institute in the world to do systems biology. And I'll just say at that point, an enormous fraction of my colleagues thought systems biology was hype and actually had no real meaning, was not going to bring anything substantial to the world. And I just pointed out to them at that time, you know, when molecular biology came to the fore in the late 60s and the early 70s, that's exactly the attitude the biochemists had. And I pointed out the biochemists who persisted in that attitude are pretty archaic today. And we'll say more about that again later. And then finally, taking systems approach to disease led to systems medicine, the thing we call P4 medicine. Now, I will say from the point of view of innovation, I really did learn major lessons. I'd say 4 major lessons in creating paradigm changes. So the first was each of these changes did fundamentally change how we thought about biology and the practice of biology. There was no question about that. I would say for each one of these 5 changes, there was enormous initial skepticism. And in some cases, actual hostility because there were perceived threats to the traditional way of getting things done. I think a third area, and I think this is really important, is none of those paradigm changes could have been realized unless you created new organizational structures. That is, I would argue no one of those paradigm changes could have been done in the context of pre-existing scientific structures because of bureaucracy. And I'll say a bit more about that later. And then the final point I would make about paradigm changes is it absolutely requires enormous risk-taking. And I think that's something that's very fundamental, as I'll say at the end of my lecture, to any entrepreneur. If you really want to do something new and transformational, it absolutely requires taking risks. So let's talk about each of these 5 in turn very briefly. The instruments, it doesn't really matter what they are, that we developed, 4th at Caltech and the 5th here at the University of Washington, really are the framework for doing contemporary biology. But the really important point that they made was that they introduced the idea of high-throughput biology and of big data in biology. And, you know, big data is the common word, but it was clear biology was going to have big data 20, 25 years ago. It's just now we're really getting in the point to create that big data and everything. So we did it through the automation of the chemistries, these 5 different technologies, integrating together the chemistries, and then miniaturizing and parallelizing the chemistries. And that's exactly what contemporary technologies are doing more and more with microfluidics and nanotechnologies, where in the future you won't have a room like this filled with DNA sequencing machines to do a lot of sequencing. You'll have a desktop machine that can do more than the entire room could before, just to give you the idea of the kind of changes that are coming. Now, as we were developing these instruments, beginning in the late 70s, I had a friend come and say, why don't you commercialize these things? And so I went to the president of Caltech then, Murph Goldberger, a physicist, traditional academician, who gave me this really stern lecture on the role of academic institutions is scholarship and education, and it's not commercialization. And I said, well, I viewed it in a different way. I argued what you were really doing is transferring knowledge to society, and creating companies is one of the most effective ways that you can do that. And he was infinitely skeptical, but said, okay, if you want to commercialize things, you do it on your own. So I said, okay. So for the next year and a half, I went to 19 different companies of one sort or another with the vision of these first 4 instruments that we had. And it was a really compelling vision. I mean, as clear then as it is today. But I will say at the end of that period of time, 19 out of 19 companies were uninterested. And in fact, it was Bill Bowes, a venture capitalist who became a good friend from San Francisco, who called me at the end of that period and said, well, let's start a venture company. So I went back to Murph Goldberger again, and he said, venture money's dirty money. Academic institutions don't want to get involved with venture money. And at that time, Harvard was having a to-do with Mark Potashny and Tom Maniotis over at Genetics Institute. But I wore him down, and finally, after a couple of months, he said, okay, I'd persuaded him there was no other alternative. But faithfully, what happened was we had a meeting of the board of trustees just before we were to sign the venture agreement. And Arnold Beckman was chair of the board at that time, and he came to this meeting, which I spoke at on the vision of these 4 instruments. He came running up to me afterwards and he said, this is incredible. This is just what Beckman Instruments needs. Well, it turns out because Beckman was on our board, I'd gone to Beckman Instruments 3 different times trying to argue that they should take on these instruments. And the 3rd time they said, we understand what you're pitching, we're not interested, don't come back. So I said, well, Arnold, I don't think your company's very interested. Anyway, he flew up the next morning, and his employees shaded the truth, and I'll leave it at that, created a very, very complex situation, which ended up getting resolved, but it was not resolved easily. But I learned 2 really interesting lessons from that. Lesson number 1 was, with this really new vision and new idea, if any one of those 19 companies had accepted, they wouldn't have done 100th the job. A new company dedicated entirely to that, who could, and this is the really important point, who could hire the very best people to execute. And that's what's key about new organizations. The second point I learned that was equally valuable is if you have a vision, never take it to middle-level management. They're interested in P&L. You go right to the top and you say, look, here's what I want to do. I mean, Arnold got it in a microsecond. And in retrospect, I thank God I didn't go to Arnold first because, again, Beckman would never have done the same job. This company called Applied Biosystems that we actually created. So again, we needed a new organizational structure to really achieve the vision here. And from that, I went on, as you heard, to start a series of other companies. And again, I was always interested in, have we done things that would be useful for society, and could you create companies out of them? And I'll just say, of the 13 companies that are listed here, only 1 failed, so that's really quite a spectacular record. Some have been very good, and some have been okay, but only 1 failed, and that 1 failed for it. The idea was great, the CEO was a disaster. And in companies, we all know CEOs are what success or failure is going to hinge on quite often. So the Human Genome Project really did transform biology in a number of ways. And in fact, I've made a list of 18 ways it's transformed biology. But I won't belabor that point with you, but I'll tell you some of the major ones. One, it democratized the genome. That is, it gave any biologist access to any part of the genome very easily. Number two, it created the complete parts list that was necessary for systems biology. We know all the genes, and by inference, we know the proteins. And that's, you know, we think back to the Rube Goldberg device. The first thing we did was to get the parts list and so forth. Number three, it really laid the foundation for personalized medicine, and we'll begin to see just how that is in a few moments. And number four, this is really the first major project that embedded 5% of its budget on ethical, social, legal considerations. Now, I have to say, frankly, I think they really did a terrible job with the money, but the principle was absolutely right on. So a really key question is you can have great ideas, but if you don't get good people to execute it, they still can fail. It raised the issue which we have today in spades of big and small science. I'm going to talk about that a little bit later on. And the Battelle Institute has estimated that it has generated close to $800 billion worth of opportunities against an initial investment of $3.5 billion. I'd say that's a pretty good ROI. So, and we have a chance. We're pushing another project now called the Human Proteome Project, which in principle could be of similar magnitude. And finally, it really established this fascinating genetic point that there are no race-specific genes. And so that means our most fundamental traits are generally not genetic, but rather they are environmental. They come about as a consequence of a lack of opportunity for jobs or education or healthcare or many other kinds of things. And hence, if you think about Iraq and Afghanistan, the worst possible thing you could do to correct these offenses against people is go to war. You absolutely embed in permanency terrorism. So I think that's a really fundamental principle that the military would do, well, it's not the military, the political would do well to learn. So cross-disciplinary biology. As I said, when I developed the automated sequencer, I realized how important all these different flavors of scientists were, and went to a different president, Tom Everhart at Caltech, and said I'd like to start a cross-disciplinary department of molecular biotechnology. And he was in favor of it, and the engineers and chemists were in favor of it, and the biologists vetoed it. And you know, I never quite understood why they did. I think it was probably competition, but anyway, they did. So Bill Gates and the University of Washington gave us an opportunity to start molecular biotechnology, where we did bring together all these different flavors of scientists. And it was a spectacularly successful department. We pioneered two of the major technologies in this emerging discipline called proteomics. We developed the software for the Human Genome Project. We developed new cell sorters that could do marvelous kinds of things. And here we developed the inkjet technology. We had 2 of the 16 centers for sequencing the human genome and everything. And quite clearly, we'd set the framework for being able to do systems biology, because to do systems biology, you need this cross-disciplinary framework. But there again, the idea of can you do really new ideas in old organizational institutes really reared its head. And I would say the thing you have to understand about bureaucracies and large organizations is they've been honed by the past, and they just barely can deal with the past most of the time. Have trouble in some cases with the present, and certainly find it impossible to deal with the future. And that was what I found, quite frankly, at the University of Washington, which in many ways is absolutely a marvelous educational institution. But it was encumbered by bureaucracies that placed limitations on really innovative and novel new approaches to doing science. And that was the reason we went to create the Institute for Systems Biology. And again, we get back to deconvoluting complexity. So I'll talk very briefly about systems biology, give you a sense of what it is and how it's a holistic approach to disease and so forth, and tell you how the technical platforms we've created are not only engines for discovery, but they're engines for innovation. Very powerful engines for innovation. And then we'll talk about how we look at transferring knowledge to society, how we think about national and international strategic partnerships, and then I'll show you that I think we've really been successful using two different metrics. So a systems approach then to understanding a radio, again, gives us a really nice analogy. Suppose you were an engineer and you wanted to understand exactly how a radio converted radio waves into sound waves. What would you do? It's exactly like the Rube Goldberg apparatus. You'd take the radio apart, you'd study individually the components, and the Genome Project with the complete parts list let us do this very effectively for human beings. But what you'd realize is once you had all the parts and once you knew what the individual parts could do, you knew nothing about that conversion process. Because the real key is to put the parts in their circuits and to understand how the circuits individually and collectively created that conversion process. And it's exactly the same for human beings. We have biological networks that capture and transmit information, and we have to understand how they operate and the nature of their dynamics. And that's the essence of what systems biology is all about. So at ISB, we are about inventing the future. We are about doing new kinds of science, but we're really about transferring knowledge to society and creating strategic partnerships as well. So let's talk in turn about each of those, and I'll give you just a snapshot of how we start to think about disease, and we'll talk a little bit more completely about it later. But one of the things that is really going to be true for patients in the future is each of you are going to be surrounded by a virtual data cloud of billions of data points, many different types of data, and we'll have the computational wherewithal to integrate these data together to create models that will be predictive with regard to optimizing wellness and minimizing disease. And that is the medicine of the future, and frankly, the medicine of the future is here. We already now, today, can get your genome sequence, which is 6 billion features to begin with. Its dimensionality can be reduced considerably, but we have enormous amounts of data. So how are we going to convert data into knowledge? That's the really challenging question. Now, one of the ways that we're going to do it is to realize that these biological networks we talked about aren't unique individual entities, but they are a series of hierarchical levels of networks that operate from the molecular and cellular level all the way up to the social networks that we create as human beings. And networks at each of those levels are critical to assess in the context of health and disease. And in fact, it's these network models that let us deal with enormous signal to noise. And it's these that let us begin creating the first models for optimizing wellness and disease. What about these platforms that I talked about? Let me just give you an idea of how powerful this systems-driven platform is. And the really important point is you can think about virtually any discipline and map what I'm going to say about biology onto other disciplines. And we'll talk about that at the very end. So the idea is, I always believe that leading edge biology mandated the need to develop leading edge technology to open up new areas of, say, patient data space so you could explore new dimensions, new opportunities, and they in turn required complementary analytic tools to handle the information. And if you could have biology drive technology drive computation, you could revolutionize biology. And we've already begun to see this with the, for example, the Human Genome Project. But what is really important to do that is you need this cross-disciplinary environment, because to develop the technologies and analytic tools, you need computer scientists and engineers and mathematicians and theoretical physicists and the like. So having this platform of cross-disciplinarity is absolutely essential. But those people must be able to do two things. One, they need to speak one another's languages so they can communicate effectively. And two, they need to be able to work together effectively in teams. And that's not something academicians do well. And if you put all that together, you can create lots and lots of interesting new knowledge. But this engine is also an engine of innovation, because at every turn of this cycle that I've talked about, you create new innovations that are the substrate for possible company creation. And I'd argue, if you go through the list of the 13 companies I showed you earlier, there are examples of companies that emerge from every single one of these junction points between biology driving technology, driving computation, revolutionizing biology. And of course, analogous to what the Genome Project did, systems biology has really democratized both the technologies and the analytic tools for being able to handle big data. And I think that is one of the really transformational aspects. What about transferring knowledge to society? How does ISB view its role there? Well, I think what is about ISB, the Institute for Systems Biology, is that it has actually created 3 special organizations for transferring knowledge to society. So one is the Center for Inquiry Science, which is embedded directly within ISB itself. And there we have 7 full-time people who work on K-12 science education. And I think we've really transformed education at the Seattle school system over the past 15 or 16 years. And I'm not going to talk much more about that, but it is critical that we have both an educated public, an educated workforce, and that we stimulate those few percent of the students who could go on to become scientists and engineers, and this is the way to do it. The second point is we've created a 501c3 nonprofit called the P4 Medicine Institute, which is working together with ISB to create a clinical network of medical centers that will attack pilot projects in systems medicine to be able to demonstrate the power of systems and P4 medicine. We'll say a word more about that. And then, as some of you may know, we started back in 2003, 2004, the Accelerator, which really was a company to create new accelerators. So if you think about ISB, it's spun off 5 companies in the 12 years of its existence, and they're all doing extremely well. If you think about the Accelerator, it is a joint venture with 5 VC groups, ISB and the Accelerator, and together in that time, since 2004, we've created 17 companies, of which 12 are still functional and so forth. So if you look at the bottom line, ISB has been involved in 17 companies. It's raised, now it's getting close to $500 million in capital, and it's generated a workforce that's approaching 450 or something like that at this point in time. So it has had an impact on especially the local region right here. Strategic partnerships for ISB are really critical because federal funding, at least from conventional sources like NIH and NSF, is very limited in funding big science projects. And a lot of what we're interested in is big science. And that's why we've turned to strategic partnerships. And the idea here is that you can actually find organizations that have enormously complementary skills and materials that you need. But more than that, with a shared vision, you can think about entirely new approaches to fundraising and transforming big science. And I'll give you one example of that later. I will say, starting about 7 years ago, I realized that these international strategic partnerships were really going to be key. And I spent the next 3 years going to 5 different companies and came very close with every one of them. But in the first 4 cases, there was always one really interesting point. So I know more about strategic partnerships, I suspect, than anyone. But the 5th turned out to be a spectacular success, and we'll talk about that a little bit later on. So what about metrics for success, to give you an idea of what we've done? When we started in 2000, as I said, I'd say the bulk of my friends were really skeptical about systems biology. So it was gratifying when, in 2010, the National Academy of Science came out with a report on the new biology, and the new biology was systems biology. And they said they didn't want to call it systems biology because that would refer too much to the institute and so forth. But what was interesting is 2 of the 11 people on that committee were among the greatest skeptics at the beginning in 2000. So people can change their mind. Another much more direct measure of success is a Spanish institute that has developed new metrics for assessing the impact of papers and then integrating the impact of all papers for each institution to give you single metrics, and then comparing, in this case, in the latest one, 2012 ratings, 3,290 institutes. So for the 2012 measure, ISB, by the quality metric, came in 4th in the world, and I think that's really quite a remarkable accomplishment for a small institute that's now 12 years old. But it shows the impact that systems biology has had in every single dimension: biology, medicine, computation, and technology. And we've had very high impact papers in all of those areas. So what about systems medicine and P4 medicine? I would argue systems medicine already is beginning to transform how we practice medicine. Now, there are lots of medical schools that don't realize that yet, but it's happening all around them. Through using systems approaches to understand disease mechanisms, through using family genome sequencing and so forth, through making blood a window into health and disease and stratifying disease and stratifying patients, and being able to take completely new approaches to identifying drug targets, which is going to save an enormous amount of money in the drug business and everything. So P4 medicine then is the convergence of systems medicine with patient-activated social networks and the big digital revolution. And the 4 Ps, predictive, preventive, personalized, and participatory, are really transforming, again, virtually every aspect of contemporary medicine. And in fact, if you really summarize what systems medicine and P4 medicine are really about, it's 1, quantifying wellness, and 2, demystifying disease. And in fact, we're now working on a proposed next company, a wellness company, that is going to integrate all of the data from the individual of 3 major different types and use that to create models that can optimize wellness and minimize disease. And we're going to create databases over time that will allow us to mine for the wellness strategies and technologies of the future. So I think P4 medicine has 4 interesting implications. Turn around the escalating costs of healthcare. It's going to digitalize medicine in interesting ways I'll mention in a moment. It's going to make every single sector of the healthcare community revise their business plans, and if they don't, they'll become dinosaurs. And there are a fair number of pharma companies that I think are headed definitely in that direction. It's going to transform the practice of medicine, but even more important, it's going to create enormous wealth in the future. I'd argue in the 10 to 15 year period, there will emerge a wellness industry that will far exceed that of the healthcare industry, and there's an incredible opportunity here right at the very beginning. That's why we're excited about the wellness company I talked about. Why are we going to save money? Early diagnosis, the ability to take a disease like breast cancer and say there are 5 different types and then do an impedance match against the proper drugs, re-engineering disease-perturbed networks with drugs, new approaches to drug therapy, the benefits of wellness, the benefits of this big digital revolution that's coming. Do you realize that there are probably 70 gadgets out there that will let you measure parameters of yourself that will cover virtually every classical aspect you can think about, from sleep and the quality of sleep to the more conventional kinds of things. And of course, all the other medical advances that will be coming too. There are technical challenges, there are sociologic challenges to bringing P4 medicine to patients. I would argue the sociologic are far the more challenging of the two. And we are bringing it to patients through strategic partnerships. So one is a partnership we had with the state of Luxembourg, and we were able, over a period of 5 years, to get $100 million for developing the tools and strategies of P4 medicine in return for giving them a lot of things. Now, if I've been at the University of Washington, could I have ever made an agreement with a foreign government? I suspect it would have been pretty tough. Number two, the P4 Medicine Institute has begun to create with us this network of clinical centers for the pilot projects in Ohio State, and Peace Health, the local community hospital, our first two customers in this vein. So let me run through very quickly take-home lessons for students, faculty, and administrators. One, systems thinking is going to transform education in many different ways. And I think more and more we want it in education and teaching, get away from the details and the vanity of professors telling you about their favorite area, to conceptual teaching and thinking analytically and thinking outside the box and all these other kinds of things. I think it's key for everyone to be cross-disciplinary, and that's business, that's financial, that's legal, that's everything. And it's really key to teach students to think outside of the box. I mean, how do we do that? It's really an interesting question, and we really are failing. There are very, very few people that think really effectively outside of the box. I would argue the academicians' roles are fourfold: scholarship, education, transfer of knowledge to the community, and community leadership, which is something we haven't talked about, but I feel quite strongly about. And for the students, and frankly for some of the faculty, my philosophy about career success is summed in this thing Thornton Simon once told me. That is, the average person has a bell-shaped curve. They go to a peak and fade away. But what's interesting is if at the peak you have the courage to actually start all over again, you can have another accelerating phase, and you can keep on doing that as long as you have the courage to change. It's only when you get pegged into a hole that you end up with a bell-shaped type of curve. So 6 concepts. One, I talked earlier about the idea that you need new organizational structures, and you need to be capable of taking risks. I think there's going to be a globalization of every field and discipline, and I think those people who can reach out to their superb counterparts wherever they are in the world and form strategic partnerships will be in a unique position to attack the really big problems of whatever their discipline is. Big science and small science is enormous debate back at NIH and NSF, and unfortunately they take the view that big science is bad. I would argue the two are enormously complementary, but I'd argue even more, it's only big science that can really solve in an integrated way challenges. And again, let's think about this idea of complexity, because I'd argue it's a major challenge for the 21st century for all disciplines and not just biology. And there are a bunch of reasons why biology can really solve its complexity now, and it has to do with these systems approaches. But what's interesting is if you ask yourself, what are society's major challenges? They are healthcare, global health, nutrition, agriculture, energy, environment, and so forth. And I would argue it's only through big science, through systems-driven, integrative, cross-disciplinary approaches that you can really attack these problems. And I think the challenge for academic institutions is how can they create these environments in the context of what has existed in the past. I'd say the systems approaches can be applied to virtually every discipline you want to think, and especially company creation. And I would argue that what I believe is fundamental for innovation from the individual are these systems approaches to things, thinking outside the box, being willing to take risks. I think determined optimism is absolutely fundamentally essential. And I think the only way you convince the world is you have to have enormous passion for your vision, for your ideas and things. So this is a Chinese symbol for the way, and I would argue systems thinking is the way for dealing with the complexities of science and society and fostering innovation. Thank you.